Hi everyone, myself Mrs. S. Nusrath Najeeba, Assistant Professor, Department of Computer Science SF, the Standard Fireworks, Rajanatharam College for Women, Sivahasi. In this video lesson, we are going to learn about the acid properties in DBMS. Let's see it. Let's go through with the contents first. First, we are going to see about what is an acid property and why we need an acid property. Then we are going to see the acid properties in detail. After that, we are going to see the impact of acid properties in DBMS, then its use cases, that is examples and advantages. Finally, we are going to see the conclusion. Okay, let's see what is acid property and why we need acid property. Okay, in database management system, transactions are the fundamental operations that allow us to modify and retrieve data. To ensure the integrity of a database, it is important that these transactions are executed in a way that maintains consistency, correctness and reliability even in case of failures or errors. This is where the acid properties comes into play. Okay, what is acid? Let's see it clearly. The word acid itself, in this, A stands for atomicity, C stands for consistency, I stands for isolation and D stands for durability. Okay. Acid features, these are used by the DBMS to maintain data integrity and consistency. The atomicity, consistency, isolation and durability are the basic concepts ensures that a database transactional integrity. For developers working with relational database systems, understanding acid characteristics is critical. They act as checks and balances for acid properties database transaction to ensure accuracy and reliability. Let's see the properties clearly. First, atomicity. What is atomicity? It means a transaction is all or nothing. That is, either all its operations succeed or none are applied. If any part fails, the entire transaction is rolled back to keep the database consistent. There are two cases in this. First one is commit, second one is abort or rollback. Okay, what is commit? If a transaction is successful, the changes are applied permanently. Okay, then rollback or abort. If the transaction fails, any changes made during the transactions are discarded. Let's see with an example. Here, consider the following transactions. T consists of T1 and T2. That is, transfer of $1,000 from account X to account Y. If the transaction fails after completion of T1 but before completion of T2, the database would be left in an inconsistent state. With atomicity, if any of the part of the transaction fails, the entire process is rolled back to its original state and no partial changes are made. Okay. The next property is consistency. Okay. Consistency means in transaction that the database must remain in a valid state before and after a transaction. That is, the database must remain in a valid state before and after a transaction. A valid state follows all defined rules, constraints and relationships like primary keys, foreign keys, candidate key, super key, etc. If a transaction violates any of these rules, it is rolled back to prevent corrupt or invalid data. If a transaction deducts money from one account but doesn't add it to another in a transfer, it violates consistency. Let's see an example for this. Suppose the sum of all balances in a bank system should always be constant before a transfer. The total balance is $700. Okay. After the transaction, the total balance should remain $700. If the transaction fails in the middle, like updating one account but not the other, the system should maintain its consistency by rolling back the transaction. So total before T occurs 500 plus 200, that is 700. Total after T occurs 400 plus 300, therefore it will be 700. Next property is isolation. Isolation ensures that transactions run independently without affecting each other. Changes made by one transaction are not visible to others until they are committed. It ensures that the result of concurrent transactions is the same as if they were run one after another, preventing issues like dirty reads, non-repeatable reads. What is dirty read? Reading uncommitted date. Then non-repeatable read, the data changes between two reads. The last one is the phantom reads, that is new rows appears during a transaction. Let's go with an example. Here consider two transactions T and T double dash, x equal to 500, y equal to 500. Okay. Transaction T, that is T wants to transfer $50 from x to y. So T reads y, that is value 500. Deducts $50 from x, then the new x will be 450 and adds $50 to y. So new y will be 550. Okay. In transaction T dash starts and reads x and y, that is x equal to 500, y equal to 500. It calculates the sum 500 plus 500, that is 1000. Meanwhile, the value of x and y change to 450 and 550 respectively. So the correct sum should be 450 plus 550 is equal to 1000. Ensures that T double dash does not read outdated values while another transaction is still in progress. Transactions should be independent and T double dash should access the final values only after T commits. This avoids inconsistent results like the incorrect sum calculated by the T double dash. The next property is durability. Durability ensures that once a transaction is committed, its changes are permanently saved even if the system fails. The data is stored in non-volatile memory, so the database can recover to its last committed state without losing data. Example, after successfully transferring money from account A to account B, the changes are stored on disk. Even if there is a crash immediately after the commit, the transfer details will still be intact when the system recovers, ensuring durability. Okay. Next, we are going to see the asset properties impact. That is impact on DBMS design and operation. The asset properties in totally provide a mechanism to ensure the correctness and consistency of a database in a way such that each transaction is a group of operations that act as a single unit, produces consistent results, act in isolation from other operations, and updates that it makes or durably stored. Okay. The first impact is data integrity and consistency. Asset properties safeguard the data integrity of a DBMS by ensuring that transactions either complete successfully or leave no trace if interrupted. They prevent partial updates from corrupting the data and ensure that the database transitions only between valid state. Second impact is concurrency control. Asset properties provide a solid framework for managing concurrent transactions. Isolations ensure that transactions do not interfere with each other, preventing data anomalies such as lost updates, temporary inconsistency, and uncommitted data. The third main impact is recovery and fault tolerance. Durability ensures that even if a system crashes, the database can recover to a consistent state. Durability properties: if a transaction fails midway, the database remains in a consistent state. Next, we are going to see the use cases. In modern applications, ensuring the reliability and consistency of data is crucial. Asset properties are fundamental in sectors like banking, e-commerce, and healthcare. Okay, in banking, transactions involving money transfer, deposit, or withdrawals must maintain strict consistency and durability to prevent errors and fraud. E-commerce. In e-commerce, ensuring that inventory counts, orders, and customer details are handled correctly and consistently even during high traffic requires acid compliance. Healthcare. In healthcare, the patient records, test result, prescription must adhere to strict consistency, integrity, and security standards. Now we are going to see the advantages of asset properties. Preserves data consistency, guarantee transactional integrity, provide fault tolerance, and recover through durability. Enable concurrency control between transactions via isolation. Maintain constraints and business rules through consistency. Eliminate partial transactions with atomicity. Okay. Conclusion. Asset properties enforce reliability in database transactions by maintaining atomicity, consistency, isolation, and durability. They prevent database corruptions by bad transactions and provide recoverability after failures. However, they all introduce performance costs due to concurrency restrictions. Despite their limitations, asset principles are essential for any robust database management system. Thank you for watching the video.